Bismillahirrahmanirrahim. Assalamu alaikum, everyone. Today we're going to learn a very different and a new topic. It is the final topic of physics. So, alhamdulillah, we've finally made it towards the end. The only thing that we have skipped in this entire year is 16.3, which is called the electric field. And one of the reasons why I skipped it is because it is a bit of an advanced lesson. It would take an unnecessary amount of time to complete it, considering how we're on an online system now, and Bismillah, we're in Ramadan as well. I just thought we would go ahead and skip out on 16.3, and we'll start with a more interesting chapter and the final chapter of this course, which is called Circuits and Circuit Elements. So I think that you're going to find this pretty interesting. A lot of students do find this to be a very not an entertaining lesson, but they really learn quite a bit out of it. So it's a very new branch of physics. So let's go ahead and get started, inshallah. So one of the first things that we want to do is just kind of get an idea of three of the most popular words that you're going to hear when it comes to circuits, all right? And the three words that you're going to hear a lot are voltage, current, and resistance. So what I want you to just do for a moment, pretend that you had a water hose, right? Pretend you had a water hose, and the water hose has obviously water coming out of it, and there's a certain amount of pressure that it has as it comes through. So think of voltage as like that pressure of water, right? So a low pressure water, there's not much voltage. A high pressure of water has a lot of voltage. Think of it that way, right? Then current is this next thing that we define. And obviously it's got nothing to do with water, but it just helps to kind of have these images in your mind, and that's why I'm giving these to you first off, right? So think of current as the diameter, right, of that hose itself. So just think about it. If you had to move a certain amount of water through this hose, and you were to increase the diameter of that hose, right? If you were to increase the diameter of that hose, how much water would be able to flow through that now, right, as opposed to before? So think of that diameter of the hose, the size of the hose, basically as your current, right? And finally, think of resistance as basically little sand particles or something that might be impeding the water from flowing out of that pipe, right? So think of resistance as that sand in the pipe itself, right? And so you'll see these units a lot in this chapter. Volts is basically for voltage. It's hard to confuse that one. But current is measured in something called amperes, and it's A, that's the notation for it, and I is just current, right? Current. And then resistance is measured in ohms, that's after a person, and it's usually called R or it's called omega. That's called the omega symbol right there, right? Um, well, in this lesson, you're going to be learning first about schematic diagrams, and perhaps you've seen a diagram like this before, but it's a very simple setup, and I'm going to show you this in a live way in a little bit. But this student, what she's doing is basically she's connecting a battery to a switch, and then the switch is going to a bulb, and then the electrons are flowing back to the battery itself. All right. Think of it as this diagram or think of it as that diagram. But basically what we want to do is we want to come up with a schematic diagram. What is a schematic diagram? A schematic diagram, basically it takes out the battery as far as the picture of it is concerned, the bulb is concerned. Instead it comes up with a scheme. And so now the bulb is represented by this symbol. The wires are represented by just lines like this over here, and the battery is represented by these two bars, one of them being larger, the other one being smaller or shorter, right? And a lot more on that to come. So what we want to do is just kind of, I'm going to show you guys a really cool diagram in a little bit. But what you want to think as we're going through it is I want you to think of water as it's being pumped, right? Water is pumped, and as that water flows through this pipe, that water might encounter some sand, but eventually it'll go back into that pump again. Okay, so every time you open this faucet, it'll come through. Now, the reason why we give you that water analogy is I want you to think of electricity like that, right? So it's because these are all, they're electrons, so it's hard to imagine how this works, right? No matter how many diagrams we make, you don't actually see it. You can't touch it in that sense, right? So voltage is basically like that water. Sorry, the voltage is basically that difference in the high pressure and the low pressure. All right. So you notice how this is higher, that's lower, right? So that voltage is created by the battery, just like the pump creates that pressure difference. The battery creates that voltage difference, right? And so that voltage, it's once it differs, there's a current that flows through the circuit. It goes through the light bulb and then it comes back. So by the time it comes back, there is no more potential energy that it's got, and we'll talk about that in a moment, right? But it's got no more electric potential, and so then the battery's job is to repump that current, and again send those electrons through, right? Now, as a diagram, here's what that would look like. You would show a battery with that symbol. You would show current with the symbol over here. And then you would show what is called a bulb or a resistor with this symbol over here. All right. Now, that gets kind of confusing for students, even with the analogies and all. So what I've got here is I'm going to make for you a circuit. And if we have some time, inshallah, in this year, things are a little bit tough right now, but if I get some time, we can design a lab where you can experience this by yourself. Otherwise, khair, inshallah. Students generally haven't even gotten to some of these lessons that we've managed to teach surprisingly in a time where there is no school, right? But here, what I'm doing is I'm taking pieces of wire, right? I'm taking pieces of wire, and I'm making a circuit for you. And you are welcome to try this by yourself as well. I have left a link for this same exact app. It's a very cool app. My kids love to play with it all the time. They think it's interesting. And now I'm going to create a battery in this circuit. Okay, so that's a copper wire that's running. You'll notice that there's these little electrons that are showing. So we'll just kind of move that out for now, right? So there's really nothing showing. And then what I'm going to do is I'm going to connect wire like this, and then I'm going to connect wire like this over here. It doesn't have to be a square. We just kind of leave it as a square just so people understand what's happening, right? So you may have noticed that as soon as I connected that battery to that wire, the battery, it bursted, right? What's happening here? Well, basically what happened is the current from that battery, it flowed through and it came back to the battery and it bursted the battery. The internals of the battery were busted because of that current. Now you might be wondering, wait, I don't understand. Why would something like that happen? And most students, they don't understand it in the beginning, right? So let's cut this right now for a moment and let's try to show some current. Okay, let's try to show some current. So think of these electrons as your current. Okay, think of that as like your water, right? And now I'm going to quickly connect this, and what's going to end up happening is these electrons, they're running straight through that battery, and that battery cannot contain it, right? And so what it does is it actually bursts. Now, that's perhaps not the simplest way to explain circuits. You're like, wait, you just made a bad circuit, right? And in a sense, I did, just to show you a certain thing. Now, what if instead we put something called well, everybody knows what a light bulb is, but let's connect a light bulb somewhere in this circuit. Okay, so I'm going to break the circuit here, and I'm going to connect a light bulb, right? So these wires will connect to the light bulb like this, and then this wire can just outstretch and it can connect to the bulb. Now what you'll notice is all of a sudden the battery's not lighting on fire anymore, right? It's not bursting. Why is that? Like now it's actually there's something actually working through it. And look at where the electrons are actually flowing, right? Look at where the electrons are actually flowing in this particular direction. And so that gets a little confusing for people to accept. And so what we do is we look at a conventional way of it when we speak about current. And current, in a sense, is actually the opposite way as what electrons would flow. So I'm going to press this button here called conventional, and now there's red arrows. And so this right here is the current. Okay, it's the current that we say. Think of it as the water that is flowing through that diagram, and then it's coming to the bulb. Okay, and then it's going through the bulb. Okay, now what if we were to disconnect the bulb? All right, what if we were to disconnect the bulb and then we were to move that bulb out and reconnect these wires? You recall what happened is the current would be too much and it would make the battery light on fire, right? So for that, one thing that we come up with, we're like, wait, why don't we introduce a switch? All right, why don't we put a switch in the system? So something like that might, you know, not occur all the time, but what happens, this is an open switch. When you close the switch, again, you have a problem, right? So that's not going to work for us. So what do we really do? Do we just put light bulbs every time? That's not really the smartest thing to do because light bulbs take up a lot of energy. You'll learn that you want to keep the amount of energy that you have relatively less, right? Otherwise, things heat up. So you can't just put light bulbs everywhere in your circuit, right? What can you do? So here is the tool that we use. It's called a resistor, all right? And a resistor, we started off the lesson talking about, you know, resistance, and we talked about, think of it like sand, okay? So what the resistor does is it causes that flow to slow down somewhat, all right? And now if you take a look at that switch being closed, there is a current that is flowing from the positive terminal of the battery. This is the positive terminal of the battery, and it's going through the resistor, and now the battery is not bursting. So you need resistance basically for something to flow. Now, resistance is measured in something called ohms, all right? And that as a symbol is omega. Now, what if I were to increase the amount of resistance? Just think about it. If you were to put more sand in a water hose, what do you think would happen to the current? All right, so just start thinking about that. You'll notice that as I'm doing this, the colors are changing. That's actually how they tell resistors. They change the colors on them. So this is actually real. This is actually how it looks like. They don't come with numbers written on them. So notice what happened. When I increase the resistance of this circuit, look at those arrows are barely moving anymore. What if I were to decrease the resistance to something that's relatively smaller? And there you go, now it bursted again. So what I'm trying to say is just because it's resistance, see, this is how the water analogy is not the best because nobody wants to have sand in a water hose, right? But in this case, resistance is absolutely necessary. You actually need it, right? You actually need for something like that to occur. Now, you're probably thinking you're spending a lot of time on this. Really, this is the lesson in a nutshell, okay? And what we can do is we can say, all right, what if we connected a fuse, right? What if we connected a fuse in this system over here? Oops, sorry, I didn't give it enough time. So if I connected a fuse, here's what happens. All right, here's what happens. Let's open the switch so it doesn't do that. A fuse is basically designed to prevent fires, right? It doesn't want that current to flow back into the battery and then destroy the battery because that creates a fire. So what a fuse does is it takes the hit instead, and that's why it's called a fuse. So let me flip the switch here. And notice how the battery is totally safe, but the fuse, which initially looked like this over here with the little element that's still working, now it's a broken element. And so that fuse, when it breaks, that's how a person can tell, oh, this thing is fused. They just look at through the little glass tubing and they can tell that something has fused, right? So a fuse has that particular purpose that we use, right? Um, and so that's, there's a lot of stuff that you can explore by yourself. But one last thing, and one very important thing that we need to do before we leave this, is basically, how are you going to draw this stuff, right? This is the whole purpose of this lesson is to talk about schematic diagrams, right? How are you going to draw this? You can't just like keep doing, just keep drawing like cool looking batteries and resistors. I mean, you know that I can't do these things myself, right? So let's think of a way to do that, all right? So here goes. I'm going to click on this button down here. And what this button does is it switches up. Let me open the switch real quick. It moves from this notation, right, to a schematic notation, which looks like that right here. So these are the schematic diagrams, right? And what you really want to do is you want to look in this left column and just get used to it. So a wire just looks like line. A battery, recall this is where the battery was. So the positive terminal is this terminal. The smaller terminal is the negative terminal, right? And then a switch looks like this. So when you flip the switch, the current flows, and then when you open the switch, that's what it looks like. Then one of the most important things is the resistor, right? The resistor looks like a zigzag within the current. Within the circuit itself, and you're going to make several of these. You're going to make a lot of these as you go through this lesson, so just kind of get used to it. Recall this was the light bulb, right? We don't really have it connected right now, but this was the light bulb here. And so the light bulb looks like what you see here. And when you turn it on like this, you can see it a little better. But when you do it like this, you can't really tell that the light bulb is on necessarily, right? But, you know, there's that. Um, so those are the handful of things. And a fuse, that's a little beyond this lesson, but a fuse looks like this over here. And you can change the rating on a fuse as well if you have to, all right? Now back to our lecture over here. So basically, one more thing that I want to mention is you probably have heard of AC and DC, direct current and alternating current. What exactly is that? Think of it like this, right? If something is direct currents, it says if current were like water in a hose, DC would flow in only one direction. It just goes in one direction, okay? Current, if you're looking at it over time, look at this graph over here. Current is just going in a certain direction, all right? And things that use direct current are like your computer and stuff like that, okay? Now, on the other hand, AC, which we use as I have my laptop plugged in just now, I'm looking at it, is in alternating current, you're sending it back and you're getting it back. You're sending it forward, you're getting it back like that. And so in fact, not surprisingly, it can actually, it looks like a harmonic motion, and so it can actually be modeled by a sine curve, okay? And for that, transformers, you probably, if you've ever been on a road trip, I'm sure you have, you look out on a road trip and you see these massive looking structures. Those are called transformers, okay? And so they use alternating current. Obviously, your plugs that you have in your houses, those use alternating current as well, where they send current back and forth. And it's a little beyond the level of this course or this discussion to talk about more of it. But, you know, so much of this, I'm really hoping that it really makes you think. You know, you're like, man, I really want to go out and learn a little bit more about this. And especially if you've never learned anything about it, I'd really recommend that you go in and you think about those things. Um, this is just a piece of the book that I want to make sure that you read. Most of it I have explained it to you through a picture, but you need to know basically what symbol stands for what, okay? And the book does a really nice job of explaining that, so I'm not going to go much into that right now. But basically, there's one thing that we did not talk about, which is a capacitor. One thing you want to know about a capacitor, because what we did, we actually skipped a certain lesson. Chapter 17 had capacitance in it. Okay, so what exactly is a capacitor? A capacitor, what it'll do is it'll essentially store the charge, right? It'll take the charge, it'll act like some kind of a battery, okay? It takes the electrons, right? And notice how a battery looks like this. What it will do is it'll take that charge, it'll store it on one metal plate. And then the other metal plate is basically put a certain distance apart from it, okay? And then when you need to, you can take that thing that's basically storing electrons and then release them, right, in different kinds of ways. But that's as much as you need to know about capacitance, all right? Now, a few just kind of notes to make about this lesson. Number one, short circuit is a very big problem. And I showed you a short circuit. What does a short circuit look like? A short circuit was basically when you did not have let's take this resistor out, all right? And let's take that bulb out of that picture as well. Basically, in a short circuit, what had happened, switch this on, is as soon as that current ran through, you shorted that circuit. Okay, so a short circuit, obviously, it's a problem for us, and the fuse, its job is to prevent the battery from blowing out. Number two, the source of potential difference and electrical energy is the circuit's EMF. So that's one thing that you need to know really well. EMF, it stands for electromotive force, all right? So what's causing those things to actually move through? That's called the electromotive force, and that's EMF for you, okay? But then the other thing that's written here, and I want to discuss with you, is called a potential difference, okay? It's called a potential difference. Now for that, I have a slightly different diagram that I want to show to you. Again, because this is such a new topic, it just really helps students to kind of wrap their mind around that. So what I want you to think about is the following. You've got you've basically got let's start from this side over here, okay? I want to see if I can zoom in a little bit. Just give me one moment. All right, very good. So this diagram took me a while to find, but it's a really good diagram, right? And basically what it's saying is there's a battery pump, all right? So there's a pump, like a water pump, right? And what it's doing is it's taking these charges and it's raising them to the top. So that's what a battery does, okay? That's what a battery does. And then what happens is they go around and then they go through a water wheel, and that water wheel is used to do work, right? It takes up energy. And so what happens is as those charges are coming down, right? As they're coming down, they make that water wheel spin. So what we're trying to explain to you here is after that, they've lost all their potential energy. Remember when we learned potential energy, we said if something was at a certain height and then it fell, now it has zero potential energy. That's what we're trying to explain here, except this is called electric potential energy. So those charges are being raised by the battery. So they give those charges the battery gives those charges a potential. So they're able to do work, right? And then once they're done doing that work, they have no more energy. They need to go back to the battery, and the battery is going to pump them up again. And that's why the battery is the most important character. Without the battery, they're going to die. All right. Now, that difference that's occurring, you see that difference between the top and the bottom, that's called the potential difference. Okay, that's actually what we refer to as a potential difference. And another word for potential difference that we give is we generally call it voltage. Okay, so the voltage of a battery is its potential difference. So this writing over here says the source of potential difference in electrical energy is the circuit's EMF. So the battery serves as that electromotive force. It's the thing that moves those charges along. All right. Now, one thing that you just want to know is for conventional current, the voltage that we have is a little less than the electromotive force. And read up on this, please, to understand what it's really talking about in this situation. But what I can give you is just to understand a little better. Basically, this battery here, it actually has its own little bit of resistance. Okay, a battery is like has a little bit of sand in it by itself. Think of it that way. Okay, so what happens is it's like saying the water pump has sand in it, sort of a thing, right? So what's happening is this battery behaves as a small little resistor. But if you read here, it says, for simplicity's sake, in problem solving, it will be assumed that this internal resistance is insignificant. So it's interesting. Remember when we learned something like kinematics or forces, we said that there is no air resistance. Pretend that air resistance doesn't exist. Well, guess what? Now that we're learning electricity, because everywhere in physics there's going to be some level of resistance. So now that we're learning electricity, we say that ignore that bit of resistance that the battery has. All right. The only resistance we focus on is the charge, is the resistors that we put in the circuit. All right. Now, potential difference across a load equals the terminal voltage. Now, what exactly is a load? All right. A load would be something like this water wheel right here. Okay, that constitutes the load. Um, if we talk about that diagram that we had earlier and we put this diagram back together again, now this light bulb behaves as the load. All right, so it behaves as the load. Now, when it says potential difference across a load equals the terminal voltage, basically what they're trying to say to you is whatever voltage is going through this circuit. All right, so now I'm going to show you some values. All right, now I'm going to show you some values. All right, so here you've got 9-volt battery. You've got a 9-volt battery. Let's put some of these things away because we don't want to confuse anybody. So I'll put the fuses away. I'm going to put that fuse away too. Now, you got a 9-volt battery, all right? That's telling you how much it can create of a push for that current to flow. Now that light bulb has a resistance, right? It's resisting that current. That doesn't mean it's going to push it back the other way. It's just slowing it down, okay? It's slowing down. And so as that current flows through, that right over there, let's take a look at the voltage by using what we call a voltmeter, okay? So a voltmeter measures voltage and an ammeter measures current. All right, so we'll measure current later. We don't want to confuse you with that right now. But what we'll do is we'll take a voltmeter, and the way a voltmeter works is you connect one of the LEDs to the beginning part of, between one part and another part of, Bismillah, the circuit. So before the electrons, before the current flows in, and then after the current flows out of that resistor, this is how you connect the LEDs. So one LED goes to before it goes to the bulb, one LED goes to after it goes to the bulb. So you see how it says 9 volts. And that's what it's trying to explain to you when it says potential difference across a load equals the terminal voltage. All right, so that difference between it is going to equal terminal voltage. Now, one last little comment is if you were to take those LEDs and put one here and take the other LED and put one here, you see what it says? It says 0 volts. What does that mean? The potential difference between where I connected this LED and where I connected the other LED is 0. The 9 minus 9 is still 0. You understand? But why was it not 0 here is because now all of that current, it went through, pretend this is like the water wheel, and those electrons or that charge, it flows down. And when it flows down, the difference between this part of the circuit and that part of the circuit is now 9 volts. And so when we say that the potential difference is equal to, across the load equals the terminal voltage, that's what we're referring to, is however much you have on that battery, it's going to be dissipated so that by the time it comes back in, you got nothing left, right? So if you connect now again, the LED's over here and the LED over here, notice how it says 0 volts, right? If you connected it over here and on this side of the circuit, now it says 9 volts. So what we're saying is before it gets to the light bulb, it had 9 volts. After, it's got a lack of 9 volts. That's always going to happen as long as your battery's 9 volts. If you were to increase the voltage of your battery, look at what happens to that light bulb. I increased that voltage to 50, right? Now there's the currents flowing faster, right? And look at what the voltmeter is reading on the voltage meter right here. You're probably wondering, what if you were to continue to make this a more powerful battery? And I would really like to, entertain that thought. Look at the battery is a 120 volt battery, and look at how fast that current is actually flowing through, right? Isn't that very interesting? Um, and if you were to disconnect this battery, right? If you were to disconnect this battery and you were to connect a much more powerful battery, this is a 1000 volt battery, right? And this 1000 volt battery, you can increase it to like 100,000 volts right there, and you can take this resistance, take a look at that battery's on fire. What are we trying to say is that little bit of sand particles is not going to do for a battery a battery that's that strong, right? Now, if you decrease the voltage, it'll work for you. So, it's a really interesting combination of voltage, current, and resistance. And initially, when we learn this, there's always a bit of confusion among students. What's the difference between the three? And more on that, inshallah, as we continue through this lesson. Okay. I want you to watch a little video, a couple of videos that I have connected. I will ask about this eventually, but basically, what's a transistor? It really has changed our world. I come from an age where there were not cell phones and things were not, just kind of so technologically advanced. And now, subhanallah, what a entire room full of computers could do back then, now a simple little calculator can do. So how does that work? How do transistors work? You really want to look into this. It's a very interesting topic. Anyway, so thank you for listening to this lesson and this lecture, and have a nice day, inshallah. Assalamu alaikum.